Imagine burning through like 1 billion computing tokens.
Oh, yeah. Which is just a massive amount of processing power.
Right, processing power, time, and money. And all of that just to teach an AI how to act like a manager for, what, 100 simple update steps?
Just 100, yeah. It's incredibly expensive.
It's staggering. But that cost is, that's the reality of the AI frontier right now. We aren't really dealing with just a single AI brain in a jar anymore, right?
No, not at all. The cutting edge has completely moved on. We're looking at multi-agent systems now, or MAS.
MAS, right. Which, for you listening, these are essentially entire virtual corporate offices just bustling with specialized AI workers.
Exactly. You've got like one AI searching the web, another doing math, maybe another one debating logic.
But to make that whole virtual office function, somebody has to be the boss.
And being the boss of a multi-agent system is, well, it's arguably the most complex job in artificial intelligence today.
Because it's not just answering the prompt directly.
Right. The orchestrator doesn't solve your query itself. Its job is to look at this complex problem and basically draft a blueprint.
It has to figure out who to hire, right?
Exactly. Which sub-agents to use, what specific instructions to feed them, and how those agents actually need to communicate to reach a solution.
Which brings us to the core of today's deep dive. We are looking at a really fascinating excerpt from Architecting Intelligence, the GenAI Research Compendium.
Specifically focusing on a state-of-the-art foundational paper.
Right, from the researchers at Rutgers University and Salesforce AI Research. And it's titled, A Reward Modeling for Multi-Agent Orchestration, or OrchRM.
OrchRM, yeah. And the researchers here, they really set out to solve this massive bottleneck.
Like, how do you train this AI boss to draft smarter workflows without just completely bankrupting yourself on computing costs?
Because the current way is just not sustainable.
Okay, let's unpack this. Why is the standard way of training these orchestrators so, fundamentally broken?
Well, the standard training methods simply weren't built for teams. Historically, we've relied on things like reinforcement learning from human feedback.
RLHF, right? The classic thumbs up, thumbs down.
You know the drill, yeah. A human looks at an output, gives it a thumbs up or a down, and the model adjusts.
Which works great for, like, making a chatbot polite.
It works beautifully for a single chatbot. But try asking a human grader to look at a massive, highly dynamic routing graph of 6 different AI agents interacting in real time,
right,
and then asking them to instantly determine if that specific workflow structure was optimal.
A human wouldn't even know what they were looking at. It would just look like a giant bowl of digital spaghetti.
Precisely why human annotation fails here. The interdependencies are just way too complex for us to evaluate easily.
So if you can't use humans to grade the blueprint, what do?
The industry default has been what's called a full sub-agent rollout.
A full rollout. What does that actually look like?
Basically, you let the orchestrator write its plan, and then you actually execute the entire workflow. You spin up the search agents, the math agents.
The reflection agents.
Exactly. You let them run all the way to a final output, and then you just check if that final answer is correct.
Okay, so if we translate this to the physical world, it's like paying a massive construction crew to build an entire skyscraper from start to finish.
Right.
Just to see if the architect's initial blueprint was any good. And if the building collapses,
you just tell the architect to draw a new blueprint.
And you pay the crew to build the whole thing over again. That seems wildly unsustainable.
It is the absolute definition of wasteful. And, it's the exact reason that MES Orchestra framework we mentioned earlier burned through over 1 billion tokens just for 100 update steps.
Just to update the manager 100 times.
Yeah. Every time you want to give the orchestrator feedback, you are paying the token cost for every single sub-agent that worked on the project.
That is painfully expensive.
But beyond the financial cost, full rollouts create this severe credit assignment challenge.
Oh, I can totally see that happening. Like, if the final answer is wrong, if the skyscraper falls down, whose fault was it?
Exactly. Did the architect write a terrible blueprint?
Or did the architect write a perfect blueprint, but the math agent just, carried a 1 incorrectly?
Or did the search agent hallucinate a piece of data on step 4? You just don't know.
Right, because you only grade the final output.
When you only grade the final polished answer, the orchestrator receives this very blunt pass or fail grade for a massive group project.
Oh, like getting a C on a group project when you did all the work.
Yeah, exactly. It doesn't get clear, targeted feedback on what specific part of its routing plan was actually flawed. So the learning signal is incredibly noisy.
So we need a way to grade the blueprint itself, right? without pouring the concrete.
And that is exactly where OrchRM enters the picture.
So the researchers basically built an AI trained to act as like the ultimate architectural inspector.
Yes. Instead of running the whole team of subagents to see if a plan works, OrchRM evaluates the quality of the orchestration plan directly.
Like before any subagents are actually fired up.
Before a single token is wasted on execution, they trained a reward model, which is a dedicated scoring function that just reads the orchestrator's proposed workflow and assigns it a quality score.
Okay, so if the score is high, you proceed.
Right. And if the score is low, the orchestrator goes back to the drawing board to write a better plan.
But wait, if humans are terrible at grading these complex blueprints, how on earth do you train this new inspector model to know what a quote-unquote good blueprint looks like?
You just remove humans from the grading loop entirely.
Really? Completely?
Completely. Through self-supervised learning, the researchers dug into the intermediate artifacts, the raw training logs and checkpoints of orchestrators that had already been trained the expensive way in the past.
Ah, okay, so they mined all that historical data.
Right. They mined those execution logs to create win-lose pairs of blueprint.
So they're feeding the model pairs of workflows and saying, hey, this one is the winner, this one is the loser, figure out why.
Exactly.
That sounds a lot like the Bradley Terry model used for chess rankings, right? Where you compare two players to predict who is better based on historical matches.
That is the exact mathematical optimization objective they used.
Oh, wow.
Yeah. By doing these pairwise comparisons, the model learns the underlying variables that actually contribute to a win.
Okay, so how do they construct these pairs?
They did it in two distinct ways. The first is specialized over base.
Specialized over base, meaning what?
Meaning they took a workflow drafted by a highly trained, specialized orchestrator, and they paired it against a workflow drafted by a naive, untrained backbone model.
Okay, well, the specialized model is the obvious winner in that pair, right? I guess that teaches the inspector what structural sophistication looks like.
Exactly. It learns what a smart layout looks like. The second pairing method is correct over incorrect.
Okay, that one seems pretty straightforward.
Yeah. They looked at past logs where the system did perform a full rollout. And for a single prompt, they found a blueprint that ultimately produced the right answer.
And paired it against a blueprint from the same model that produced a wrong answer.
You got it.
Okay, looking at those two pairing methods, my instinct would be to just use the correct over incorrect pairs. I mean, isn't getting the right answer the only thing that actually matters?
You would think so, but no.
Really? Why even bother mixing in the specialized over base pairs then?
Because if you only train the inspector on correct versus incorrect outcomes, the model has a very high tendency to overfit to the final result.
Overfit. Like it learns the wrong lesson.
Right. It might start prioritizing blueprints that look like they lead to an easy answer, but it misses the nuanced structural logic required for truly novel, complex problems.
Okay. That makes sense.
And on the flip side, if you only use specialized versus base pairs, the inspector might just learn to prefer overly complex, convoluted plans over simple ones.
Even if the complex plan is totally wrong.
Exactly.
So it would start rewarding the AI equivalent of, like, corporate bureaucracy, just adding more agents and more meetings because it looks specialized.
Exactly the danger. And that is why the data mixing ratio is so critical here.
So what's the magic ratio?
The researchers tested various combinations, and they found that a 3-to-1 ratio created the best results.
3-to-1, meaning what exactly?
3 correct over incorrect pairs for every 1 specialized over base pair. That specific mix created the clearest separation between effective and ineffective plans.
So it forces the inspector to understand that success requires both structural sophistication and functional accuracy.
What's fascinating here is that this entirely avoids human aesthetic bias.
Oh, that is a great point. When humans annotate AI outputs, we heavily favor readability, don't we?
We absolutely do. We like well-formatted bullet points, a polite tone, nice formatting.
But an AI subagent doesn't care if a prompt is polite. It doesn't need a please and thank you. It just cares about execution logic.
Exactly, and by relying purely on execution logs and mathematical pairings, OrchRM strips out our human bias completely.
It creates a scoring system rooted entirely in functional reality rather than, human perception.
Yes, exactly.
Okay, here's where it gets really interesting. The theory sounds airtight, right? But the source material provides the actual receipts in the appendix.
The test rollouts, yeah, they are very revealing.
They threw some incredibly difficult test rollouts at an untrained base model and an OrchRM trained model just to see what would happen. So let's look at the first example from the AAE 2025 benchmark.
Right, which is a notoriously rigorous mathematical competition.
The specific problem they use asks for the area of a finite region bounded by the plane x plus y plus z equals 75.
Subject to some incredibly strict interlocking inequalities.
Right, it was like x minus y is less than y minus z, x is less than z minus y. Just hearing those constraints induces math anxiety for me.
Oh, absolutely. It requires deep geometric visualization combined with very complex algebraic reasoning.
So the base model looks at this prompt and decides its blueprint will feature a debate agent.
Okay.
And it assigns two roles to this debate agent, a geometric analyst and an algebraic solver. Which, on the surface, that sounds like a totally reasonable approach.
It sounds highly plausible to a human, sure, but the execution logic is a disaster.
Why? What goes wrong?
The base model's blueprint lacks the specificity required to manage those very tight interlocking constraints. In fact, during the rollout, the base orchestrator actually triggers a system error.
Wait, a system error, like it broke.
Yeah, it literally outputs system error, redundant XML blocks detected. It formatted its own internal instructions incorrectly.
So it's failing a basic management communication.
The two subagents immediately lose the thread. One starts incorrectly projecting the region onto an xi plane, completely ignoring the strict inequalities.
Oh no, and the other one?
The other tries to derive random side lengths. They conflict, the system just panics, and it outputs a wild guess of 1017.
Just a random guess.
And in a separate run, it guessed 303.
Complete system collapse. And the actual ground truth answer is 510, by the way.
Right.
Now, let's contrast that failure with the trained model, the one guided by the Orch-RM inspector. It tackles the exact same problem, and it also opts for a debate agent structure.
But the blueprint is remarkably nuanced this time.
Yeah, instead of just generic math rules, it sets up a geometry specialist and an inequality expert.
Notice how the trained orchestrator identifies the actual friction point of the problem there.
Inequalities.
Right. The core tension isn't just geometry versus algebra. It is the specific interaction between the geometric plane and those strict inequality bounds.
And because the roles are so tightly defined in that blueprint, the subagents don't step on each other's toes.
They stay in their lanes.
Yeah, the transcript actually shows the geometry specialist identifying the boundary lines of the plane, while the inequality expert simultaneously verifies the bounded region constraints.
So instead of arguing,
they debate productively. They find consensus, they utilize a cross-product calculation, and they nail the exact answer 510.
And the really impressive part, the orchestrator itself didn't do a single piece of math.
It just built the perfect team and provided the perfect environment for them to succeed.
That is the hallmark of a phenomenal manager.
Truly. Okay, so that setup makes total sense for a rigid math problem, right? Where the rules are absolute.
Sure.
But what happens when the AI is faced with something messy, something subjective, and reliant on just fragmented web data? Let's pivot to the second example from the BrowseComp Plus benchmark.
BrowseComp plus TIE. This one tests multi-hop web reasoning. It is essentially an impossibly convoluted historical trivia mystery.
It really is. It requires synthesizing data across so many multiple disparate sources. Like, the prompt is wild. You remember all the constraints?
It asks you to find a person born between 1820 and 1830.
Right.
This person moved to Germany before they were 15. In Germany, they met an English writer who was later appointed to the Order of Merit between 1902 and 1907.
It keeps going. This mystery person also served as a private tutor in the U.S., was a friend of a famous celebrity photographer, and had a street in a European capital named after them. What was their last name?
I mean, for a single AI agent, or even just a poorly managed team, that prompt is a nightmare.
It's just way too much.
It's too many disjointed facts spanning way too many decades for one search query to handle.
And the base model proves your point perfectly here. Its blueprint basically relies on one single web search agent,
Which is doomed to fail.
It crams all those historical constraints into one massive overloaded search query. The search agent gets completely overwhelmed, zeroes in on the birth year constraint, and spits out Jules Verne.
That's a classic panic response.
Right, because Jules Verne was born in 1828.
And he certainly has streets named after him. But he didn't meet that specific English writer in Germany, and he definitely wasn't a tutor in Louisiana.
The base orchestrator set its subagent up for failure by assigning it an impossible workload.
Exactly. Then we bring in the OrchRM trained boss.
Right. And it looks at this historical nightmare and instantly recognizes it as a multi-part verification problem.
It doesn't rely on one search agent.
No, it drafts a blueprint, assigning 3 separate web search agents to work concurrently.
It fundamentally parallelizes the research.
Yeah, so Search Agent 1 is instructed to ignore the noise and only look for the birth year window and the European street name.
Very narrow focus.
Right. Then Search Agent 2 is deployed exclusively to verify the childhood move to Germany and identify the English writer meeting.
And Agent 3?
Search Agent 3 is sent to investigate the U.S. tutoring records and the friendship with the photographer.
But having 3 agents pull fragmented data doesn't actually solve the prompt.
No, it doesn't.
The brilliance of this blueprint is that the orchestrator then assigns a 4th agent, a reflection agent, to act purely as the synthesizer.
The management structure is just beautiful. So the 3 search agents return with completely disjointed pieces of the puzzle. Agent 2 finds a historical move to Neuilly, Germany, and a meeting with the writer George Meredith. Agent 3 pulls obscure tutoring records from Louisiana and verifies a friendship with Nadar, the famous Parisian photographer.
And then the reflection agent takes over.
Exactly. It takes these isolated data points, cross-verifies the timeline, and correctly synthesizes the answer, which is the lycée reckless.
The execution was flawless because the blueprint was perfect.
The sub-agents were given narrow, achievable tasks.
And a dedicated synthesis layer was put in place to catch errors and combine the data. It's brilliant.
So what does this all mean for you, the listener? I mean, we've clearly established that OrchRM makes the orchestrator dramatically smarter, but did it actually solve the token wasting problem we started with?
That's the real question.
Right, because if it still takes a supercomputer to run this intelligent boss, it doesn't really democratize this technology at all.
Well, the efficiency gains detailed in the study are honestly staggering, and they apply to 2 different phases of AI deployment.
Okay, what's the first phase?
First, let's look at test time scaling. This is when you give a system a prompt, and instead of just generating one plan, it generates, say, 10 different possible blueprints on the fly to find the best approach.
Well, generating 10 blueprints sounds pretty expensive.
It would be if you had to execute all 10 of them. But because OrchRM evaluates the blueprint before execution, it acts as an instant filter.
Oh, I see.
It scores all 10 plans, tosses the bad ones, and only executes the winner. During this test time scaling phase, using OrchRM improved accuracy by up to 8%, while using 10 times fewer tokens than traditional methods.
10 times fewer tokens just during the generation phase. That's a massive cost reduction for everyday use.
It is.
What about the training phase?
That is where the real magic happens. The second phase is trajectory-level training.
Which is how researchers continually update the core weights of the model over time, right?
Yes, to make it permanently smarter based on its past execution paths. When they used OrchRM to continually train the orchestrator on that messy BrowseComp Plus dataset, it achieved better performance while using 46 times fewer tokens than standard methods.
46 times fewer tokens.
Yeah, it dropped the training cost from 1.6 billion tokens down to tens of millions.
That is an insane drop.
We are talking about reducing compute time from weeks on a server farm down to hours on standard hardware.
Wow. If you are running AI tools for a small business, or conducting academic research, or even just trying to automate complex workflows in your everyday life, computing power translates directly to money.
Absolutely.
If it costs 1 billion tokens to train a specialized multi-agent system, only the massive tech monopolies get to participate in the frontier. But OrchRM fundamentally lowers the barrier to entry.
It really does.
We can now have highly complex multi-agent AI teams solving rigorous problems without needing a Silicon Valley budget to operate them.
It is a profound step toward democratizing advanced reasoning capabilities. But, as with all foundational research, we do have to acknowledge the limitations the authors transparently outline.
Right. It's not a magical plug-and-play solution for every single problem just yet.
No, we are not at the point of an omnipotent universal AI manager. Currently, these reward models are highly domain-specific.
Domain-specific meaning they only know what they're trained on.
Exactly. You cannot take an OrchRM inspector trained to grade rigid mathematical blueprints and ask it to grade open-ended web search blueprints.
Because the logic is completely different.
Right. The underlying orchestration patterns, the logic of why a workflow succeeds are just too different. If you try to mix math trajectories with history trajectories right now, it creates severe noise in the training data, and the reward model completely loses its predictive power.
So for the time being, you need to train a dedicated architectural inspector for math workflows and a completely separate inspector for history or coding workflows.
Furthermore, the model's performance is entirely bound by the quality of the data it learns from.
The historical logs.
Right. If the initial training logs you feed it don't contain diverse, high-quality examples of successful multi-agent interactions, the reward model won't actually learn what true success looks like.
Garbage in, garbage out.
Essentially, yes. It can only optimize based on the ceiling of its training data.
Even with those limitations, though, moving from building the entire skyscraper to just grading the blueprint is a quantum leap in efficiency.
It truly is.
Well, thank you for joining us on this deep dive, but before we go, I want to leave you with a final thought to mull over. Something inspired by the paper's emphasis on early-stage intervention and removing humans from the grading loop.
It's a big shift.
We just spent this deep dive exploring how we are successfully training AI orchestrators to independently judge the quality of a workflow plan before any action is even taken. And we've removed human graders because our brains are just too biased by things like readability, while the AI is infinitely better at grading pure execution logic.
But what happens in a year or two? When these orchestrators start designing entirely new, hyper-complex sub-agent structures that human minds literally cannot comprehend. If the AI becomes the ultimate judge of the AI's blueprint, and the blueprint is written in a structural language we can no longer even decipher, who is ensuring the building is actually safe for humans to enter? Something for you to ponder until next time.